Okay, let me talk about Puerto Vallarta and cosmic rays. This year is the 125th anniversary of the great Mexican cosmic ray physicist Manuel Vallarta, who provided an explanation for the latitude development of cosmic ray intensity through the famous Lamater-Batara theory. Professor Vallarta completed his bachelor's degree, PhD degree from MIT in 21 and 24, and eventually become a professor at MIT. He mentored Dick Feynman and was a co-author of Feynman's first paper. He worked with Louis Alvarez and Arthur Compton to establish cosmic rays are predominantly protons. The venture of this conference is named after his maternal grandfather, and I want to thank Sunil Gupta for providing this very important information for me. Accelerators has been developed for 400 years. The earliest accelerator on the left still exists today, perhaps at a very low energy, perhaps has done the most important experiment. The largest accelerator on the ground is the 27-kilometer proton collider with extremely high energy to study the fundamental building blocks of nature. After 400 years, we know atoms have electrons outside. Inside the nucleus, there are protons, neutrons, and particles. Inside the particle are quarks. So my first encounter with particle physics is my first experiment to measure the size of electrons. Modern electromagnetic theory by Feynman, Schwinger, Tominaga in 1948 required that electrons have a zero radius, namely no measurable size. The theory agreed well with all experiments until a 6 billion electron volt electron accelerator built by Harvard and MIT provided the most sensitive measurement of the size of the electron. The Harvard experiment was done by world's leading experts in the field who has spent many years to develop the technology of use intense photon beam to measure electron size. At that time, the largest electron accelerator is a 100 feet Cambridge electron synchrotron. So you have an electron rotating in a magnetic field, you generate 6 billion electron volt electron. And so a photon go on the lower left shows the photon go to the field of the nucleus, produce electron-positron pair. And so you have a virtual momentum transfer, delta P. Delta P times delta R is H bar, and therefore you measure the size of the electron. This is the very famous Harvard experiment 64. The measurement, the red point, compared with quantum electrodynamics, which based on electron has zero dimension. Clearly, you can see at the distance between 10 to the minus 13 centimeter to 10 to the minus 14 centimeter, there's a deviation from quantum electrodynamics. And therefore, the data show the electron has a radius between 10 to the minus 13 to 10 to the minus 14 centimeter. Most importantly, the experiment was independently confirmed by a very famous group at Cornell Electron Accelerator. Since those results touch upon the foundations of modern physics, I decided to perform the experiment with an independent method. At that time, I'd never done an experiment by myself and knew nothing about electron physics, so I received no support in US. In 65, I decided to leave Columbia University, where I was an assistant professor, and move to the newly built 6 billion electron volt electron accelerator in Hamburg, Germany. This is the accelerator complex in Germany today. When I was there, the electron accelerator was quite small. It's in one of the buildings. So this is looking from the top to the bottom is the experiment of measuring the electron positron pairs. A photon from the synchrotron with the intensity of 10 to the 11 per second on a 10% target, and that means you have an equivalent luminosity of 10 to the 35, produce electron-positron pairs, and they are going through the magnet and then going through position-defining counters and go through velocity measurement Cherenkov counters, finally in the shower counter, which measures the energy. This design was quite different from all the traditional design at that moment. The first is we're using only dipole moment and counters to measure the momentum. The momentum is measured by trajectory in a magnetic field. Second, most important, is we use two Cherenkov counters to identify electron positrons. Because the background is enormous, so you need to put two Cherenkov counters so the electron generated by pion from the first counter would be swept away by the magnet, not into the second counter. Third, we use a calorimeter to measure the energy. Most important, none of the detector sees the target, so that they're not exposed to neutrons and gamma ray background. To reject large pion background, you require momentum measured by magnet equal to the energy measured by calorimeter. The acceptance of the detector is defined by counters and not by the traditional way from the edge of the magnet, because the edge of the magnet is the source of background. So this is the first spectrometer I made in Hamburg. There were two students on the left, was for many years later on the Dean of Research at Princeton University. In 1966, after 8 months, our group completed the experiment in Germany and discovered the electron indeed has no measurable size. The radius is less than 10 to the minus 14 centimeter. What is plotted on the y-axis is all result compared with the theory of Feynman, Schwinger, Tomonaga, and see they are in perfect agreement. So the result was first announced in 65 at the Rochester Conference at Berkeley, now known as the International Conference on High Energy Physics. On this occasion, I met Penofsky, Feynman, and Rabi, and these three had played a very important role for many years in maintaining a good relationship with me. So this was the first paper we published by ourselves, validity of quantum electrodynamics at small distances. And most of people from DAISY, plus 3 people at Columbia University. And on the left is a control room. Now it's the size of your iPhone. On the right is after the result was announced, and there's a traditional German celebration of drinking beer. So my first lesson in doing experimental physics is do not always accept the results of experts, because I know experience where people at Harvard, at Cornell were world-class experts. When you measure the electron-positron pair with the photon, you have an electron-positron pair invariant mass. When the invariant mass reach 700 GeV, you see a deviation from quantum electrodynamics. When you reach 1 GeV, you have another deviation. This is not a deviation in quantum electrodynamics, but the fact a photon has turned into a massive particle, rho omega phi. And rho omega phi go back to photon, go to E plus E minus. So my second class of experiment is photons and massive photons. Photon has a mass 0. Rho is a 2 pi resonance, has a mass close to 1,000 MeV. Omega is a 3 pi resonance. It has a similar mass. Phi is 2K resonance. It's also similar mass. The important thing is photon and heavy photon have same quantum number. With J, angular momentum is 1, charge conjugation is -1, priority is -1. Therefore, you can imagine at high energies, when photon interact with the nucleus, can be visualized as photon go to rho interact with the nucleus. Or photon goes to omega, photon goes to phi. And this, at that time, was known as vector dominance model. Namely, the interaction with photon with nucleus is replaced by rho omega phi interact with the nucleus. The experimental question is, what is the relationship between photons and heavy photons? So then I left Columbia and joined MIT, and in Hamburg, they helped me build exactly the same detector, but with much more precision for coordinate resolution and particle identification. So let me give you 2 examples of photon and heavy photon. One of them is observation of coherent interference pattern between rho and omega decay. Rho is a 2 pi resonance. Omega is a 3 pi resonance. Therefore, they do not interfere in the final state. So a photon goes to a rho, look the Feynman diagram, and rho scatter from nucleus, go back to a photon, go to pi plus, pi minus. And they do not interfere with the omega scattering from nucleus, go back to photon, go to 3 pi's. But in the electron-positron mode, it's different. A photon can go to a rho scatter from nucleus, can go back to photon, go to E plus E minus. And so was omega. Since this interaction, if it exists, involving alpha to the 3rd order, so the branching ratio is very small. And so the pion rejection becomes difficult. And this has been, everybody predicts this should exist, and nobody has found it. And so this is our observation of the interference pattern of photon on beryllium on major E plus E minus. Our major data are the yellow point for rho to electron positron pair alone without interference the red data. The red curve clearly do not agree with the data. Only rho omega interference can explain the measurement. Another observation at that time considered quite important is the observation of forbidden omega to 2 pi decays. Photon goes to a rho in the field of nucleus, decay to pi pairs. They do not interfere with the photon goes to omega to 3 pi. Okay, because 2 pi does not interact with 3 pi. But photon goes to a rho, goes to 2 pi. Photon can go to omega. Omega can go to a photon, go to a rho, go to 2 pi. And therefore, in the extremely rare case, a branching ratio 1 part in 10 to the 4, they do interfere. And this was a very interesting subject, and there were many Nobel laureates, Glashow and Stamberger and others, all work on this, and nobody were able to see this. With the precision detector, we see or measure data, the yellow points, and do not agree with rho to pi pi. They agreed with rho omega interference to pi plus pi minus. 10 years in the field to find this. So my second lesson for experimentalists is precision instrumentation with multiple redundancy is vital. Other previous experiments were inconclusive. The third experiment is the observation of new form of matter. We learn that photon and heavy photon transform into each other. We'll also learn how to use high-intensity flux of 10 to the 11 gamma rays per second. 10 to the 11 is a high number. We'll learn how to reject pion by a factor of 100 million. We also have a mass resolution about 5%. So the question is, why should there only be 3 heavy photons or a mass of 1 GeV? So we decided to answer this question by conducting an experiment at the Brookhaven National Laboratory. So this is the proposal 598 to Brookhaven National Laboratory. And it stated the best way to search for vector meson is through production experiment of the type proton-proton goes to a vector meson which decay to E plus E minus. The reason are vector meson are produced by strong interaction, thus you have high production cross-section. And second, you can use high intensity, high duty cycle extracted beam. Namely, you can take all the accelerator beam on your target. Third, E plus E minus experiment limits the quantum number to a photon, thus enable us to avoid measurement of angular distribution of decay product. I stated, contrary to popular belief, the E plus E minus storage ring is not the best way to look for vector mesons. In the E plus E minus storage ring, the energy is well defined. A systematic search for heavy meson requires a continuous variation and monitor of the energy of 2 colliding beams. A difficult task requires almost infinite amount of machine time. Storage ring is best suited to perform detailed study of vector meson parameters once they are found. At that time, the prevailing theory is study strong interaction. And there are 2 proposals of quark models. Nobody paid too much attention. One is by Merrill Gell-Mann, shows what happens if you have a charge 1/3 and 2/3. Another is by George Zweig. George Zweig called it ACES. And third was by Yuval Ne'eman of Israel. And this, at that time, were one of the many models used. We certainly did not start the experiment to look for quark model. The Brook experiment is an experimental challenge. First, you need to change the orbit of the accelerator you take on the left. You can see 10 to the 12 proton per second on a 10% target. At this energy, the multiplicity is 10, and therefore you have 10 to the 12 particle produced. Of the 10 to the 12 particle per second, the most difficult to observe, the rarest, are the electron-positron pair. The electron-positron pair compared to pi pair is less than 10 to the 8. And therefore, you for 1% experiment require 1 in 10 to the 10 rejection. What does a 1 in 10 to the 10 rejection mean? During rainstorm over Mexico City, there are about 10 billion drops per second. You try to find one drop that is rare. And that's why it was considered very, nearly impossible to do. The experiment was not popular with the physics community. Most of physicists believe that the search for heavy photon was not the most interesting research topic. Nobody interested in quarks, and nobody thinks to look for heavy metal has any physics meaning. Most of the experimentalists believe that such a difficult experiment could not be carried out. So most of the major accelerators rejected our proposal. Finally, the proposal was accepted by Brookhaven National Laboratory on Long Island, New York. So this is the experimental layout of, and the top view is the upper graph, the side view is the lower graph. You can see a beam on a target, M0, M1, M2 are magnets, C0, CE are Cherenkov counters, A0, A, B, C are position determined proportional chambers. So looking from the top, there's no bending. You measure theta. Looking from the side, the magnet bends things up and measure momentum. So the detector design is exactly the same as we've been using for years in Hamburg, but it's decoupled measure momentum and angle, so have best mass resolution. Two very important instruments were designed at that time. To reach a rejection of 10 to the 10, we used Cherenkov counters. So the best Cherenkov counter to separate electrons from protons is low index of reflection, namely gas hydrogen. Gas hydrogen, however, produces very few photons and also is explosive. And so we designed and built 4 Cherenkov counters with the end 125 microns thick. The light is collected by 1 meter in diameter spherical mirror for 2, elliptical mirror for the other 2, with the thickness of 3 millimeters to reduce multiple scattering. These 4 Cherenkov counters were made by Marcel Vivajean and Jean-Jacques Robert of Annecy Laboratory, and they worked with them before, so they supported us with these counters. They were made at CERN machine shop. Another precision detector was designed by Ulrich Becker, who worked with me since the beginning. Since there are 20 megahertz of particle passing through the detectors, to sort out multiple tracks, we use the fact if you have an equalizer triangle, you have A1 plus A2 plus A3 is equal to B1 plus B2 plus B3. In this way, you can sort out the signal from the background. This counter will later exhibit in Smithsonian Institute in Washington for many years. Now, let me talk about radiation protection. We have 10 to the 12 particle of proton on the target, and then we produce 10 to the 12 secondary. 10 to the 12 secondary is an enormous number. To make sure the detector can work and you can work near the detector, so we used 10,000 tons of concrete, 5 tons of uranium, 100 tons of lead, and 5 tons of salt to absorb the radiation. The 5 tons of salt is to stop slow neutrons because salt contains large amount of water. One of the difficulty I had was to explain to the government why I need 5 tons of salt. So this is the experiment. And you can see the 2 arms. The yellow part is the Cherenkov counter, and also the top of the shielding has been removed. This is the first data. Shows the mass of E plus E minus. Suddenly at 3.1 GeV, you have a sharp peak. And this was August 74. And we decided to check this signal because the rate is so low. One of the best way to check is to lower the magnetic field by 10%. Once you do that, particle bends to a different part of the detector. If the peak is false, then you will move it away. But the peak did not. What they show on the left is the magenta is 90% magnetic field, and the blue is 100% magnetic field. The fact they fall on top of each other shows you have made a genuine observation. This is a production rate of J particle at different laboratories. You can see it goes up quickly with energy. Fermilab, USSR, and CERN ISR will produce 4 orders of magnitude higher, but they did not support this experiment. And so Brookhaven was the most difficult place to celebrate the discovery of the J particle. What is the unique nature or property of J particle? Most important, the lifetime is 10,000 times longer than other particles. The significance of this is to suddenly discover in a remote region on Earth, a village where people live to be, instead of 100 years, but 1,000,000 years old. And the spectrum of the J particle decays into each other in the same way as the positonion. And there's this second observation shows indeed it is a quark model, indeed is valid, and there's a new form of quark. So this was exactly 50 years ago. In fact, this year, in November, there will be a big celebration on this discovery. The new and surprising type of atomic particle found. This is in the New York Times. Because nobody expect such a thing could exist. The particle was also observed in the E plus minus collider and the coincide. And this was continually studied for 40 years. One of the places is Beijing Electron Positron Collider in China. And this project was led by academician Yifang Wang. And on the left, it shows the collider. On the right, it's battery detector. This, on the left, shows new particle, mass 1830, when you have 58 million events, when you have 200 million events, when you have 10 billion events. And you see more particles coming out. In total, 30 new hadrons were discovered in baths from charmed meson production and decays. A more important thing is exotic hadron in the decays. So the J-go-to quark and antiquark can emit photons and gluons. Gluon can form a new particle for X2370, and also can form part 2370 is only made of gluons, and therefore is considered a glue ball. We can also make to quark and antiquark. It's a prime, and these are the evidence shown in the lower graph. So my third lesson is sometimes important to keep faith in yourself, do what you think is right, because for this experiment, I did encounter a unanimous objection from the community. The fourth experiment is the discovery of gluons. We already know inside the atom a nucleus, inside nucleus are protons and neutrons, and inside the nucleus, inside proton neutron are quarks. Binding the quark together is strong force known as gluons. So the next experiment is the positron-electron collider in Hamburg, Germany. It's a 46 billion electron volt collider. The original purpose is to verify the newly formed electroweak theory by Weinberg, Glashow, and so on. It is known as the Mark J experiment to measure the forward-backward asymmetry. And this is the earliest confirmation of electroweak theory. We have electron-positron collide via photon to mu plus mu minus. And if you have a virtual Z0, the mass is not too far away, then you produce a polarity-violating forward-backward asymmetry. The lower graph shows or measure data indeed agree with the existence of virtual Z0, does not agree with QED alone. And this was shown in the physics today, said electron interference parameter confirmed. Accidentally, we observe when you have an electron-positron collide, you produce quark, antiquark. On the way out, they become two jets, like the lower left graph. But if gluon exists, with the increase in gluon energy, you will see the growth of three jets. And if you break the three jets up in a linear scale, you see the last graph and show the blue points or data. And the data of three jets can be explained by many things. One is phase space plus quark antiquark with a large momentum transfer. Another one is just quark antiquark with a larger momentum transfer. So observation of the three jet event is interesting, but it's not meaningful. Meaningful thing is you measure enough events to make sure statistically they agree with the quark gluon model. And this was shown in the physics today of APS. My fourth lesson is be prepared for surprises in experimental results, because the original purpose of the experiment was to verify electroweak theory. We didn't even think about gluons. The fifth experiment lasted 21 years. We used 100 GeV positron collide with 100 GeV electron at the 27-kilometer electron-positron collider. The temperature when the particles collide is about 400 billion times higher than the temperature in the surface of the sun. equivalent to temperature of the Big Bang, beginning of the universe, within 10 to the minus 11 seconds. The purpose is to search for fundamental particle in the universe. The question is, how many types of electrons? What are the size of the electrons? Can electrons be divided into smaller particles? How many types of quarks? What is the size of quarks? Can quarks be divided into smaller particles? So this is a large international collaboration between 20 countries involving the United States, Soviet Union, China, India, Taiwan, and many European countries. So this is a schematic of the detector. It's about 6-story high, and outside is a magnet followed by various detectors. And the magnet weighs 10,000 tons, was done in Soviet Union. In addition, there's a 300-ton, 100,000 channel calorimeter inside, also by Soviet Union. And this was Soviet Union's largest international collaboration outside. So this is the magnetic coil. Each of them weighed 40 tons, and the total, there are 28 of them. And development of instrumentation is find a way to produce BGO crystals. BGO crystals to provide accurate measurement of photons and electrons. In 1983, the world's total production of BGO is 4 kilograms per year. For experiment which is known as L3, we need 12 tons. So most of people think you will never get this. And so one of the technical development was the production of 12-ton BGO in 3 years. On the right is one of the 12,000 BGO crystal. On the left is the 12-ton crystal. The BGO crystal are now commonly used in industry and in medicine. So this is the Scientific American picture depict the computer reconstruction of an event. The experiment is known as L3, as I just mentioned. We published 300 papers, and there are 300 PhD degree awarded. But this work of 20 years can be summarized in 4 sentences. The first, there are only 3 kinds of electrons. Electrons were familiar at household, muons, which has a mass 200 times heavier, and tau is 4,000 times heavier inside the nucleus. At this current energy range, we only have 6 quarks. More important, electrons and quarks have no measurable size. Their radius are less than 10 to the minus 17 centimeters. You remember when I started experiment, I was able to set the limit to 10 to the minus 14. So after 30 years, it lowers 3 order of magnitude. Unfortunately, all the results are in excellent agreement with the current theory of elementary particles. And so what we contribute to physics is very small. So when experiment agree with theory, what you learn is limited. It's when the experiment confront with theory, you learn something new. So my 5th lesson is large international collaboration has become a trend of many areas of fundamental research. They involve many countries of diverse social, economical origins, and often last for decades. To have a successful international collaboration, you need to, most important, choose an important topic. People collaborate with you because they're interested in the physics. To have a collaboration last for a long time, it's very, very important to give recognition to young scientists. And third is respect the diversity of your collaboration. People from different political, religious backgrounds can work together only on one subject, namely physics. To me, equally important, never compromise on instrumentation. Try to build the best detector possible. Now, the sixth experiment, which Junior and I are working together to involve Indian scientists to join, is fundamental science on the International Space Station. The International Space Station, ISS, has a dimension of 109 meter by 80 meter, weighs 420 tons. It rotates around the Earth every 93 minutes. The construction cost is about $10 to the 11. Space is the ultimate laboratory. The highest energy particles are produced in the cosmos. It's the largest accelerator, LHC, produced particles of order of 10 TeV. But cosmic ray with energy above 100 million TeV has been observed, which of course is the main purpose of your important conference. AMS is a precision magnetic spectrometer on the space station of the type used at CERN and Fermilab. There are many fundamental discoveries who opened the field of modern physics. They discover a positron, discover a pi meson, and discover cosmic neutrinos. Before the development of high-energy accelerators, discovery of charged cosmic rays have laid the foundation of modern physics, muons, kaons, lambda, xi, and sigma, and others. Currently, there are many excellent ground-based high-energy cosmic rays. There's one in Mexico, one in Tibet, at the height of 4.4 kilometers above the Earth. And then there's in Namibia, in Argentina, also ice cube at the South Pole. These are really great experiments. Then also in space, there are many non-magnetic calorimeter experiments. One of them is Voyager. This Voyager 1, Voyager 2. And I learned recently the passing of Edward Stone, who pioneered Voyager 1, Voyager 2. It's really a loss to the community. He was really a great physicist. And then there's a Fermilab, the damping experiment made by the Chinese Space Agency. And on the space station, beside AMS, the calorimeter experiment, I call it ISS screen. AMS on the space station is to study the physics of dark matter, antimatter, the origin of cosmos, and new phenomena through precision, long-duration measurement of charged cosmic rays. Charged cosmic rays have mass. They are absorbed by 100 kilometers of Earth's atmosphere. So the properties of charged cosmic rays cannot be studied on the ground. To measure charged cosmic ray, momentum and charge require a magnet in space. From the experience I've shown up to now, you can say this cartoon is absolutely correct. This time we face reality. We are not exact rocket scientists. None of my collaborators has done any experiment in space. So this is an international collaboration. And let me mention Arturo Menchaca is one of the founders of AMS from Mexico. So this spectrometer has a transition radiation detector on top, TRD, identify electron positrons. The 9-layer silicon tracker measures Z and P, followed by ring image Cherenkov counter, measures Z and E, followed by electromagnetic calorimeter in the bottom, measure the energy of electron positrons. Then there's the upper time of flight, lower time of flight, together to measure the direction of the particle and measure charge and energy. And then there's a magnet together with the rest of the detector to measure charge and momentum. So around the magnet, position veto counters to reject cosmic grid from the side. Therefore, you can see particles are measured many times. The experiment was sent to space station in 2011. From 2011 to 2025, we'll do continuous data taking. From 2025 to 2030, which is the current lifetime of space station, we are in the process next year to add 8 square meter silicon tracker on top to increase acceptance by factor 3. Let me share with you the latest results on positron electron antiprotons. They can come from cosmic collision. They can come from dark matter collision if dark matter are particles of high enough mass. Positrons can also come from pulsars or from photons interact with the magnetic field. Antiproton cannot come from pulsars. This is our measurement mass spectra as function of kinetic energy of positrons based on 4.2 million events. The low energy part can come from cosmic grid. Any model cosmic grid collision will give you the low energy part. The question is, what is the rest? What is the origin of the rest? It must come from a new source. Does not come from cosmic grid collision. You can see this 4.2 million events into two parts. Low energy part from cosmic collision. The high energy part is only two other possibilities. One is pulsar, another is dark matter, or both. This is our latest spectrum. On the top is the latest data, the yellow points are data, and the x-axis shows in the first 200 GeV, the energy is a log scale. The second part is the linear scale, so for clarity. You can see the data can be explained by collision cosmic radiation plus a 1.5 TeV dark matter collision. The data agree with this model extremely well. Unfortunately, of course, the yellow point, the error is still large. And this is one of the main reasons we're increasing the acceptance to change the yellow part to the lower blue part. And so you have a definite confirmation with the theory. More important, you should see the one at the highest energy, the one with dotted circle, because of finite energy dark matter collision cannot produce infinite energy positrons. And therefore, the existence of this point shows indeed you have a finite mass collision produce the excess. This is the property of cosmic antiprotons. The first thing is you observe antiproton proton flux show that above 60 GeV, the ratio is energy independent between proton and antiproton. Also, you see antiproton positron flux have identical rigidity dependence above 60 GeV. As I mentioned, antiproton are not produced by pulsars. Now let me show you property of primary cosmic rays. Primary cosmic rays are produced during lifetime of star and accelerated by supernova. They propagate through interstellar media before reach AMS. Measurement of primary cosmic ray are fundamental to the understanding of the origin, acceleration, and propagation process of cosmic ray in the galaxy. Then there's secondary cosmic ray, lithium, beryllium, boron, fluorine, and others. They are produced by collision of primary cosmic ray with the interstellar media. Measurement of secondary cosmic ray nuclear fluxes are important in the understanding of propagation of cosmic ray in the galaxy. This is the result of light nuclei. The flux of light nuclei, the rigidity dependent, shows primary cosmic ray, helium, carbon, oxygen have exactly the same rigidity dependence. They have one form below 200 GeV, another form above 200 GeV. Secondary cosmic ray, lithium, beryllium, boron, have their own rigidity dependence. This is an accuracy order of 1%. But they are different between secondary and primary. This is not explained by any model I know of. A heavier nuclei, neon, magnesium, silicon, primary, compared with fluorine secondary. So a hydrogen nuclei also has two distinct classes. Now let me share with you abundance of element in solar system. Element in solar system measured from sun wavelength analysis, a meteoroid normalized to silicon 10 to the 3. This is information from NASA. When you look at the relative abundance, you see oxygen is 4.8 times more than neon. Silicon is 2.4 times more than sulfur. Iron is 17.3 times more than neon. So oxygen, silicon, iron are characteristic primary cosmic rays. But on the other hand, lithium, beryllium, boron, fluorine, scandium are characteristic secondary cosmic rays. What is the secondary to primary ratio? What does it mean? Before AMS, taking into account long-standing idea, carbon is pure primary, boron is pure secondary. The B over C ratio has been used in models, in all the models, to describe cosmic ray propagation. Yet, with precision measurement, the red dot is the most accurate measurement of carbon flux. And we found the carbon flux, it's not only pure primary, which is should be very similar to oxygen, but also have a significant secondary part. So carbon is not pure primary. The question then now, is it still meaningful to use boron over carbon in cosmic ray models? This is the summary of all the primary and secondary composition of hydrogen, helium, lithium, beryllium, boron, carbon, over to sulfur. You can see only a few elements are pure primary and few in secondary, mostly are in between. And you can carry this to heavy Z. There are still 6 elements who have very little data, and most of the high Z element is accuracy larger than 1%, and this is why we want to measure the 6 elements, measure all of them, and match them to accuracy of 1%. So we have now measured 21 of the 28 elements, and you can decompose them into primary and secondary, and they form 4 groups of the 28 elements. Let me now share with you the latest result of measurement of isotopes. Isotopes are particles with same mass and different, with the same atomic number and different mass. Since P is equal to m times V, measurement P and V determine the mass. We measure the momentum with the spectrometer, measure the velocity with time-of-flight counter, and with the ring image Cherenkov counter. The ring image Cherenkov counter has 10,000 photo multiplier, and it's a very accurate measurement. You can see the measurement of ring image Cherenkov counter for Z larger than 3, measure the speed at the speed of light is 5 parts in 10,000. So you measure the velocity accurately, therefore you can determine mass. One of the paper was just published 2 or 3 weeks ago was the origin of cosmic deuterons. Deuterons and helium-3 are considered to be secondary particles. So the green line is one of the many theoretical models with deuteron as secondary particles. And the red point is our measurement, clearly much more than the deuteron's secondary particles. And this also shows the comparison in accuracy, in value, and in energy range between AMS and the other experiment. We found, great surprise, the major deuteron, the red point, has a primary part and a secondary part. It's not only secondary. The secondary part exists is 0.58 of helium-3. The primary part is 9% of helium-4. So it's an excellent fit and shows deuterium, after so many years of speculation, really is not only secondary, it has a significant primary part. Finally, let me share with you the latest result on heavy antimatter. Matter is defined by its mass m and charge z. Antimatter is the same mass but opposite charge. So if you have antimatter star, you have antideutron, antihelium, anticarbon, antioxygen. And they exist far away with enormous background. So you need a precision spectrometer like AMS to try to detect them. This is an antideutron candidate from 100 million deuterons and 10 billion protons. In the bending plane, you measure the momentum. Non-bending plane, you measure the angle. Looking from the top, you look at velocity. This antideutron candidate have a charge minus 1.02 plus minus 0.05, mass is 1.9 plus minus 0.1, just the opposite of deuterons. This is an anti-helium-4 event. Analyze this event shows the charge is minus 205 plus minus 0.05. The mass is 3.81 plus minus 0.29. It's just the opposite of helium-4. So after 12 years of data, we see for matter, electrons, 6.2 10 to the 7 million events. And protons, helium in billions, and there are others in tens of millions. For antimatter, positron will have 4.2 million positrons, 1.2 million antiprotons, and these mostly come from particle collision and plus unknown region at high energy can come from dark matter collision or pulsars or other unknown sources. We now have candidates, quite a few of them, of antihelium at a very low rate, and we're looking for anticarbon and antioxygen. So my 6th lesson is for experimentalists, it is important to be curious, enjoy what you're doing, and work hard to achieve your goal. Thank you.
Thank you, Sam, for such a fantastic presentation. I'm sure there are lots of questions. I hope you can stay on and answer some of them.
Go ahead.
Okay, so okay, one of the question is that you had mentioned that you had used a large volume of soap. So for a layman, what is the reason for using soap rather than heavy metal, which also you have employed?
The soap contains a large amount of water and to stop low energy neutrons.
Right. So it's effective in in basically absorbing neutrons, right?
Yes, yes, yes.
Okay, okay. And there's a question from Gerardo Herrera. One candidate of anti-deuteron, one candidate of anti-helium. How many expected in conventional non-sources of antimatter?
Two things. First, I showed one of the candidates, not one candidate, one of the candidates. And their rate for anti-helium, this rate is 10 to the 7. The 7 order magnitude higher than cosmic collision.
Okay, so it is 10 million times higher than what you expected.
Yeah.
Okay, okay. The another question is, how do you decide when you started out? How did you decide which detector to use in your experiment? You know, you have used a variety of detectors. So how do you decide on that?
Uh,
How do you select those detectors?
I have done many experiments. I've submitted to the audience 6 as examples. Okay. None of the experiment, most of the experiment I done for during the time I'm doing it was considered important. As time goes by, its importance gradually disappears. And but there's one thing: none of the experiments are the same.
Right, right.
Okay. I try to think about the topic and try to find something interesting to do. This AMS experiment, I think it was in 1994. I was walking in the garden in Geneva, and I was thinking, I've been doing experiments on the accelerator all my life. Maybe it's time to do something new, something I know nothing about, and something people think is impossible. That's how it started. There's no other motivation.
Well, you certainly have chosen the impossible experiments and made them possible. Uh, uh, Another question is, what are the scientific, okay, I think this is a more generic question. What are the scientific implications of discovery of J meson?
Uh, for that experiment, I was awarded together with Richter the Nobel Prize 2 years later. In the citation from the Nobel Committee, it said that both of us discovered a new form of matter.
That's an absolute cracker of an answer. Okay. You know, you mentioned for this experiment, for the JSI I mean, the Brookhaven experiment, other labs turned down the proposal, but Brookhaven accepted it. Do you have any idea how this process worked? What made Brookhaven accept? And maybe others would have regretted afterwards, but what made Brookhaven accept this proposal?
I don't,
This
I have no idea. Most of the people think that at that time there are no quark model.
Yes,
People talk about pion proton scattering, this kind of things. And there's no theory behind it. And the experiment is so difficult. Nobody thinks it can be done.
right, right.
Yeah.
Okay, there is a question from actually from a colleague in India
Mhm.
and this is about data analysis, whether one should give, while analyzing data, should we give maximum weightage uh, to the data, to the self data acquisition, that is analysis of experimental data, or give importance to Monte Carlo simulations when making an assessment?
You cannot analyze at least I do not know how to analyze such a complicated experiment without using Monte Carlo.
So the answer is both are needed.
No,
Is that
so otherwise you will not know the acceptance.
That's
A
true.
very simple thing. You will not know the rate and the acceptance.
Right, right. The other thing which is absolutely remarkable is that, as you mentioned, that before L3 experiment, the worldwide production of BGO was 4 kilograms per year, and for L3, you had to produce 12 tons of BGO. How did it happen? What I mean, even in industry, it's impossible to increase the throughput by 4 orders of magnitude. So how did you do that?
Oh, I didn't do it. Okay. And I found out the difficulty. The difficulty is one of the material come from uranium mine. And most of people safeguard their uranium mines.
Right.
Yeah. And the Soviet Union strongly support this experiment and offered the material for us.
I see.
Yeah.
So it was a kind of what nowadays we call supply chain issue.
No, it's
And
if you get people interested in your experiment, they will find a way to support you.
right. There's another question. What initially inspired your interest in particle physics, and what led you to pursue a career in this field?
Uh, when I was at university, the first year, I was a mechanical engineer at Michigan, University of Michigan. And the second year, end of the first year, I had a conversation with my advisor. My advisor take a look at my grades. At that time, there were no computer. And I have great trouble understand engineering drawings. It's, object looking from the top, from the side, from the end. I couldn't draw a line straight. So my advisor said, why don't you leave engineering? You're no engineer. Why don't you study physics? And also, at the same time, study math. And why don't you forget all the undergraduate courses? Just go to graduate school, take courses. My advisor was very supportive, Professor Robert White. And so I switched to mathematics and physics. After I graduated, the university was very kind to me. They let me skip many courses. Don't take the qualified exam. And they're fairly eager to get rid of me. And I work with Uhlenbeck, who's a great theoretical physicist. Yeah. Uhlenbeck said to me, if he were to do his whole life over again, he would become a experimentalist rather than a theorist. I was quite surprised because here was one of the giants of 20th century. And I asked him why. He said, average experimentalist is very useful because you measure a number. Average theorist is not. That's a simple 5-minute conversation. Afterwards, I decided to start doing experiment.
I think you had some really inspiring teachers.
Yeah, indeed, indeed.
There is a question. It's also a general question. Why secondary particles depend strongly on rigidity?
No, this I do not know. This you have to ask theorists. So far, I don't think they offer any explanation.
Right. But it's an observed fact, basically.
Yeah, this is observed fact.
That's right. Okay. Are there any other questions? Okay. I'm just making sure that we have not missed out anybody.
How many people are attending the conference?
Pardon me?
How many people are attending the conference?
About 100.
Oh, very good.
Yeah, yeah. So, but we are distributed at different locations. But this is being streamed on YouTube and Facebook. So we are getting questions from there as well.
Very good.
Yeah. And I think we have more or less covered all the questions, Sam.
Okay.
And
Thank you very much.
before we let you go, there are many words of appreciation from audience for giving us an inspiring talk. And for me personally, the 6 lessons you mentioned are the most important ones out of this talk. I think that is something every experimentalist or every physicist can imbibe and carry with them. So thank you so much.
It's an honor. It's an honor for me to meet you people.
Thank you so much. It's honor is ours.
Thank you. Bye-bye.
Okay, please have a nice day. Thank you.
Thank you.